So in this video, we're going to go over how to use trig substitution to compute this following integral that's on the left-hand side and right-hand side, the integral of x divided by the square root of x squared plus 25, or 25 plus x squared. Now remember, for these types of trig substitution problems, there's really three big parts to these types of problems. The first thing we do is really introduce trig to help us get rid of these square root-like terms. So in particular, in this example, we have this x squared plus 25 underneath that square root. And we're basically thinking, okay, we might be able to use trig substitution here because we have some number plus or minus an x squared-like term. Now, full disclosure, in this problem we're about to do, we could actually do this problem using u-Substitution. But in the spirit of practicing trig substitution, we're going to use Trig Sub. But if you were actually doing this integral, we could do a quick kind of reminder of what are all the trig techniques, or what are all the integration techniques we have, and basically see that we could actually use u-Sub on this problem. Okay, so let's move forward with our trig substitution. The first thing do, introduce trig to help us get rid of the square root. After we introduce trig, we're going to have an integral fully in terms of trig functions. So we compute a trig integral. And then the final step is to convert back in terms of the original variable. So like I said, we have the square root of x squared plus 25 in this problem. So let's try to identify which of the following Pythagorean identities is actually going to help us out. So this is the first part to these problems, basically introduce trig. And again, what helps us out in these problems is our Pythagorean identities. Okay. So what we're actually looking for right now is underneath that square root, what type of operations do we have? So the first thing I try to look for is, well, in this case, we have this plus sign. So what that means is, in these Pythagorean identities, I'm looking for the identity in which we have that plus sign. In this case, it's the third one. The other two identities that we have basically have that minus sign in there. So we're looking like we're not going to build towards any identity using those two. So what that means is we're looking on sort of the right-hand side of what these identities are to kind of build what's underneath that square root into that form. So in this case, on the right-hand side of that identity, we have a 1 plus tangent squared. So really it looks like we're going to be building towards introducing a tangent as our substitution. So I'll just make a quick note of that. We're building towards a substitution using tangent. And again, the reason for that is, in this case, the clue we had was this plus sign underneath the square root. Okay, so in that note, moving forward with our trig substitution, what we want to do is introduce that tangent into that square root somehow. So we want to let x equal something related to tangent. However, there's one other aspect that we need to think about. So I'm just going to move this over for a second. If we focus on this square root, we have the square root of x squared plus 25. Now, the thing that will be different here, as opposed to what we basically have on the right-hand side of this identity, is the fact that we also have this 25 sitting there. We don't just have an x squared plus 1 there. We have an x squared plus 25. So in our trig substitution down below, I'm basically going to put an unknown little variable a that we're going to solve for in a moment to see what a needs to be, basically to compensate for that 25 being under that square root. Okay. So just going ahead with our substitution. Basically what I want to try in a moment is what happens if we just take this substitution and put it inside of that square root. So anywhere there's an x, I'm going to replace that with our a tangent of theta. So underneath this square root, just doing that, so we still have our a tan theta. Now just doing a little bit of algebra here. What's underneath this square root? Well, we get an a squared tangent squared plus 25. And now ideally what we'd like to be able to do is to really get it in the form of tangent squared plus 1, because that's what our identity is, of course. We need to basically take a 25 from each of those terms underneath the square root. So what we see here is, well, that means our a squared must be equal to 25 in this case. Or finally, we get that a is, well, the square root of 25, which we could equivalently write as 5. So if we let a equal 5, a squared is 25. And what that means is underneath the square root, then we have a 25 tangent squared theta plus 25. And from here, we're going to be able to take a factor of 25 out from each of those terms, so we can isolate basically 1 plus tangent squared. Now, before we actually go ahead and do that, I want us to also be sure of, well, we just called the number a was equal to 5. So when we go back to our substitution above, we can write that more specifically. So x is actually equal to a, or 5, times the tangent of theta. Since we've already defined what 5 is, or what a is, based on helping us out under that square root. So if we take that 25 from each of the terms under the square root, we get that that's 25 now times the quantity, tangent squared plus 1. And since we're multiplying two things underneath that square root, we could break that up into the product of individual square roots. So this will be, well, the square root of 25, and then times the square root of tangent squared plus 1. And from what we've seen from our identity above, we can see that, well, tangent squared plus 1, or 1 plus tangent squared, that's actually equal to secant squared. So underneath that square root, we can rewrite that as a secant squared. And again, going from there to the bottom is using our Pythagorean identity. And this is really what Trig Sub is all about. Because now that we have a square root of a trig function squared, well, we can write this as, well, I guess the square root of 25, we could write as 5, but we can now write that as just a single secant of theta. And that's really what Trig Sub is going to do in terms of these square roots. It helps us get rid of square roots through these types of Pythagorean identities. Now, I want us to practice a little bit of that algebra using these square roots and where we're basically getting rid of these. But of course, we have an integral to do from the beginning. The integral is also on the left-hand side. So let's just go forward with that integral now. The important thing that we just found was really the fact that we found what our substitution is going to be. X is 5 tangent of theta. So we're going to really continue with the integral here. So remember, we just said, well, x is 5 tangent of theta. I'll just rewrite our integral. So that's the integral of, well, x over x squared plus 25. Now that we've said x is equal to 5 tangent theta, anywhere there's an x, we can replace that with 5 tangent of theta, including that x that's sitting there in the numerator. In the denominator, of course, we did this algebra a few moments ago, but I'll just fill this in. So just plugging in the 5 tangent for the x, then we're going to square that entire thing in a moment. But the last thing we need to be sure of in these trig sub problems, we have already substituted for x. We also need to substitute in for that dx term. And similar to u-Substitution, the way that we go ahead and do that is through taking the derivative of our substitution. So if we differentiate our substitution, we're going to take the derivative of the right-hand side with respect to theta. So dx d theta is now equal to 5 times secant squared of theta. And similar to a u-substitution, we want to swap basically a dx for something in terms of our new integration variable d theta. So we're going to go ahead and solve for that dx in terms of the other things there. So if we go ahead and solve for that dx, we multiply both sides by d theta, and we'll basically find that dx is equal to, well, 5 secant squared theta d theta. So we can take that and plug that into our integral. And I'll just be sure we're on the same page. That was our previous dx. Okay, so we have a little bit of cleanup to do. So in that numerator, we see we have a factor of 5, another factor of 5. So we can pull a factor of 25 out in front right now. Then we have a tangent times a secant squared of theta, all divided by that square root business. That will get a 25 tangent squared theta plus 25. And again, we'll pull that 25 from both of those terms under the square root in a moment. And this is an integral with respect to theta. So it's doing a little bit of more algebraic cleanup here. Basically what's happening down below in that square root, the numerator stays the same. Underneath that square root, we can pull a 25 from each of those terms to break up that square root. So we have square root of 25 times now the square root of tangent squared plus 1. Again, that's how we're building that u-substitution, so we can use that Pythagorean identity. And that's an integral with respect to d theta. And just to remind us, this is really the important aspect for trig sub, is we're going to be able to substitute that 1 plus tangent squared theta for a secant squared of theta. So secant squared of theta, again, is our 1 plus tangent squared of theta. So we're able to basically substitute that in, and that'll help us get rid of the square root. So in this case, let's see what we have before we do that. We have this 25. We divide by the square root of 25. So that'll give us an overall factor of 5 out in front. We have the integral of tangent theta secant squared theta, all divided by, well, now what we have under that square root is secant squared of theta. Okay, and at this junction, just doing a little bit more of some algebra. So we have 5 times the integral now, tangent theta, secant squared theta, all over 1 factor of secant of theta. Square root of the secant squared gives us the secant theta, and that's where that square root goes. And the last thing we should do before we actually go ahead and try to compute this integral, we can cancel out a factor of secant from both the numerator and denominator. And at the end of this little algebraic cleanup, we have the integral of, well, 5 times the integral of a tangent theta, all times a secant theta d theta. So to bring us back, what we've done so far, we've introduced trig into this integral. We're able to get rid of that square root sitting there in the denominator, and we're left with an integral fully in terms of trig stuff. So we're at the stage now where we have a trig integral, and that brings us to Act 2 of these types of trig sub problems. Act 2, compute our trig sub integral. Or compute the trig integral, in other words. And I just want to mention, in this particular example, we've been practicing a lot of these trig integrals for the past couple days. So in this example, I wanted this trig integral to be something that's a little more straightforward than we normally see at this stage in a trig sub problem. So if we take the integral that we have now, the integral of 5 times tangent theta secant theta, if we look at what's in the integrand, we'll actually notice that's actually the derivative of secant. So for this particular trig integral, I manufactured this problem so we weren't bogged down at this stage, because I didn't think this stage was really anything new. We've been doing a lot of these trig integrals. This is just the second act, computing this trig integral. So the antiderivative we get is 5 times secant of theta plus our integration constant c. And at this junction, we have our antiderivative. The only small hiccup, this antiderivative is in terms of the variable theta, when if you glance on the left, the original integration variable we cared about was x. So we need to try and convert back into the original integration variable. And that brings us to Act 3. This act, convert back from our theta variable into the original, and in this case, the x variable. Now, the one thing I want us to recognize in this case, we've kind of done this procedure before for u-sub problems, and it was almost a no-brainer at this point for u-sub problems. Anywhere there was a u, we just went back and substituted what we had from the original substitution. If you remember for this problem, our original substitution, the actual trig sub that we made, was x was equal to 5 tangent of theta. So in this case, from our substitution that we made in this problem, we have x in terms of tangent. If we go and look at what we have from our antiderivative, that antiderivative is in terms of secant. So for trig sub, we can't usually just go ahead and re-plug in what we had before for our substitution like we could for u-sub. The extra little step we get to do is remember some of our right triangle and trig identities or trig relationships to help us get what those trig functions are in terms of theta back in terms of x. So what I mean by that is we really revisit the original substitution that we made in the problem. In this case, x is equal to 5 tangent of theta. We're going to go ahead and solve for that tangent term. So if we solve for that tangent term, we get that tangent of theta is equal to x over 5. And the way in which we relate this to a right triangle is remember those things where we had the tangent is equal to sine over cosine, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. So if we have sine over cosine, that gives us that tangent is equal to, well, in this case, it's always opposite over adjacent. So what that helps us do is we can write down a triangle now using that information. So defining our angle in the normal spot for right triangles in trig, we know that the opposite side is a side opposite the angle. The adjacent side is a side basically aligned with the angle. And the hypotenuse is the long side of that right triangle. And the way in which we can then just go ahead and forward is basically, well, if the opposite side is the side opposite the angle, we can just take what's in the numerator of x over 5. So x is that opposite side. Now, the adjacent side is what's in that denominator, which in this case is 5. And the last thing we do is, well, how do we get the hypotenuse? We use the Pythagorean theorem. Remember, a squared plus b squared equals a hypotenuse squared, or c squared, if you will. So in this case, we square the adjacent side. That gives us 25. We add to it the opposite side squared, and that gives us x squared. So we use Pythagorean theorem. And whenever we're trying to find the third side of our right triangle in these cases, we're always going to use the Pythagorean theorem. Okay, but what's nice about this is since we have our right triangle, we can now use this right triangle to basically give us whatever trig functions we need from our antiderivative. So in this case, what we need is we need to figure out, well, what is secant of theta in terms of that triangle? So if we just make a little note down below, because what we need here is secant only, we know that secant of theta is equal to 1 over cosine of theta. Cosine is adjacent over hypotenuse, which makes secant equal to hypotenuse over adjacent. So we just grab those sides of the triangle, put them in the appropriate place in that ratio, and that's what we have. So in this case, our secant of theta in this problem is equal to the hypotenuse, which is the square root of 25 plus x squared, all divided by the adjacent side, which is 5. So in our antiderivative, we can replace secant of theta with exactly that, the square root of 25 plus x squared all over 5. So from the previous antiderivative we have, which is 5 secant of theta plus c, we can rewrite that secant using that triangle and just plugging in what we get from that triangle, square root of 25 plus x squared all over 5. And then plus c. And that's really how we go through this process of converting back to the original variable by using a right triangle. And that would be our antiderivative. Of course, if we wanted to, we could cancel out those 5s. So to reiterate this process for trig sub, there's really 3 big parts. The first part, we figure out what substitution we need to make in order to introduce trig into this integral to basically help us get rid of that square root. And once we introduce that trig into the integral, get rid of that square root, we're left with something of the form of an integral fully in terms of trig functions, in which case we use identities, we use some mathematical massaging using trig functions to help us compute that integral any way we know how. Again, in this problem, I manufactured it, so we have an antiderivative in this case that we could easily kind of figure out because we know what the derivative of secant is. In other problems, you might have to spend a little more time playing around and trying some things out in the second stage of computing the trig integral. In the final stage, we convert back from the theta variable into the original x variable. And we typically do this by building a right triangle based off of our substitution that we made. For example, in this case, x was equal to 5 tangent. So we solved for that tangent by itself and got x over 5. And then using what we know about the right triangle relationships between trig and the right triangles in terms of opposite, hypotenuse, adjacent stuff, we could basically define the sides of the triangle appropriately.